Welcome to Spring LIB.
For this question, we're given several variables. The first one is the distance across the moon here, which is 7.5 kilometers. I call that d naught, and I convert it to meters. So it's 7.5 times 10 to the third meters. And it is 384,000 kilometers away. So L here is 384,000. It's the distance to the moon. And I converted that kilometers into meters. So it's 384 times 10 to the 6 meters. We have a focal length of 2.0 for our objective lens and a diameter for that lens of 11 centimeters. So F naught is 2.0 meters, and then a diameter, capital D, is 0.11 meters from 11 centimeters. It wants us to figure out the focal length of the eyepiece that is needed for our eyes to resolve an object 0.1 millimeters apart here. So little d is 0.1 millimeters, or 0.1 times 10 to the minus 2 meters. And it says at a distance of 25 centimeters. So in here, the distance from our eyes to the object is 25 centimeters, or 0.25 meters. Okay, so to go ahead and get started on this first part, we're going to write the expression for the magnitude of angular magnification of the telescope, ignoring the inversion of the image, which would give a negative sign. So the magnitude, m, is equal to theta over theta prime. And it's also equal to F naught divided by the focal length of the eye, F sub E. So again, F naught is the objective focal, or the object focal length. FE is the focal length of the eyepiece. Theta prime is the angle subtended by the object when using the lens. And theta is the angle using the unaided eye. So we can rewrite this equation to solve for the focal length of the eye. That's what we're asked to find here. And we find that F sub E is equal to, this is supposed to be theta over theta prime. I forgot my prime there. So theta over theta prime. So F sub E then would be equal to theta prime over theta times F naught. So now we can write the expression for the ratio of minimum resolved distance, d, and the near point of the eye, n. So we also know here that theta prime is equal to, d, which we know, divided by n, which we also know. We can also write the expression for the ratio of the object on the moon, d naught, and the distance to the moon, L. So theta, we'll get a new page going so we don't run out of room. Theta is equal to d naught over L. So therefore, we can substitute all of these values into our expression for the focal length of the eye and do a little simplification, and we find that F sub E, let's rewrite this to look a little nicer, is equal to d naught times F naught times n divided by L times D. Plugging all of these values into our expression, we find a focal length of the eye, which is equal to 9.8 times 10 to the minus 2 meters, or 9.8 centimeters. Of course, we rounded to two significant figures since that was the least amount of significant figures given in the values for this problem. Okay, the next thing the problem wants us to do is find out what the resolution limit set by the size of the object lens, that is diffraction, considering a wavelength lambda of 560 nanometers, or 560 times 10 to the minus 9 meters. So we're going to find both angle and distance for this resolution limit. The first thing we're going to do is find angle. So we can write the expression for the resolution limit, theta, which is simply equal to 1.22 lambda divided by, so 1.22 times the wavelength lambda divided by the diameter of the lens, d. But we know all of these values, so we simply plug them into this expression, and we find theta is equal to 6.2, once again, two significant figures, times 10 to the minus 6, and the units here are radians. So we can box that in as our angle limit. But what about our distance limit? So we can use the minimum resolution equation for distance, which is, let's start a new page here so we have plenty of room. R, we'll call that distance R, and that's equal to L times theta, expressing units of radians for theta. So we just simply plug our values in for L and for theta, and we round to two significant figures, and we find the minimum resolution distance is equal to 2.4 times 10 to the 3 meters, or 2.4 kilometers. We can box that in as our solution to the last part of the question.